I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
So far, we have talked about conservation of energy and momentum, and now we see how we can apply that knowledge to analyze collisions. Collisions can be divided into three categories, starting from the right. Here we have a completely inelastic collision, which means that the bodies stick together after the collision, and in this fact, this means that they have same final velocity, and these kind of problems can be solved using only conservation of momentum. For example, if V2 has arbitrary direction in xy plane, it has two unknowns. So, and those two unknowns can be solved by knowing the two equations of conservation of momentum, one in x direction and one in y direction. And by the way, let's make this notation that all of these can be solved by, in all these cases, momentum is conserved. And like I said, the completely inelastic ones can be solved using only momentum conservation, but we cannot do that in the case of inelastic collision. And that's only because we have more unknowns than we would have equations. So with two arbitrary velocities, we would have four components, but we have only two equations from the conservation of momentum. And the problem here is that in inelastic collision, the energy is not conserved either. So some of the kinetic energy of the particles or the objects is lost in the deformation during the collision, and the deformation is not recoverable. So it's a permanent deformation of the objects themselves. Unlike in the elastic collision, where the particles collide, they might deform momentarily, but then they spring back into their shapes, so they're almost acting like gliders with springs on them. And as you know, spring forces are conservative forces, so the energy is conserved. So these type of problems, the elastic collisions, can be solved by applying both conservation of momentum and energy. And that's what we're going to concentrate on in this presentation as well. And just to make clear, only on this one, energy is conserved. So there are only conservative forces in play in this interaction, and that energy can be recovered or will be recovered after the collision back to their kinetic energies. And now we'll see how we can do that. Here we have conservation of energy, and here conservation of momentum. For simplicity, we are only considering motion along on one axis. So we have two unknowns, VA2 and VB2, if we know the initial velocity, that is. So this system can be solved for both, and that gets pretty tedious because we have second order equations here for the unknowns. But fortunately, we don't even have to solve it all the way, because we are more interested in an intermediate result while we are doing this process. So if we would start solving these two, we would get the following. This relationship says that the relative velocity after the collision, that is VB2 minus VA2, is equal to the relative velocity before the collision, but it's in the opposite direction. So same magnitude, opposite direction. Here's an example that you are probably familiar with. So while playing pool, the ball A hits the ball B. So let's say this ball A is traveling 2 meters per second. It hits the ball that is standing still. So their distance is decreasing at the rate of 2 meters per second. And after the collision, you know that because the objects are of same mass, what happens in fact is that the A stops and the pole B continues, in fact, at the same velocity that ball A had. So, but in this case, the distance is increasing at the rate of 2 meters per second. So the relative velocity magnitude is the same, but the direction is opposite. And this is, in fact, just the consequence of conservation of energy. And why we wanted to have this result is that this one is much easier to use than the original formulation of conservation of energy. So here we have conservation of momentum and conservation of energy. This result holds also in the vector form and not only in one-dimensional motion as we have shown here. So no matter if the movement is two or three-dimensional, we still get this relationship. And this is in fact another definition of elastic collision. The relative velocities have the same magnitude before and after, but opposite direction. And this result will come very handy when we are doing calculations with the elastic collisions.